For the next few weeks, we're going to explore three questions. Can machines think? Are we thinking machines? And if we are, how does this affect our understanding of ourselves? For now, we need to introduce a few concepts to help us understand how we might go about thinking about minds as machines. Humans have a long history of comparing the mind to the latest and greatest technology. As humans began to develop more complex forms of automation, thinkers started to compare the mind to a mechanical clock. When computers hit the scene, philosophers and scientists began to think of minds as a different kind of machine, computing machines. The idea that thinking is computation and that a mind is a computing machine is the computational theory of mind. The whole point of thinking about a mind as a kind of machine, and as a computer in particular, is to explain and predict mental phenomena. We can do so, these philosophers think, by producing a computational model of a thought process. There are two major approaches to computational modeling, but we're going to learn the one that has been adopted by nearly all cognitive scientists. There are three levels of computational explanation: function, algorithm, and instantiation. We can get a grip on these three levels by looking at something that's not a computational system first. We can explain a boat, for example, in three ways. First, we can explain what a boat is supposed to do and the circumstances in which it's supposed to do it. The reason we have boats is for transporting people and things around. We also need to note that it's supposed to work in certain circumstances, namely water. If we put a boat up on a lift and then got it running, turned the steering wheel, we wouldn't say that the boat doesn't work. We decide whether or not a boat works when it's in the water, or when we imagine how it would work in the water. Devices are supposed to do certain things, but they are only supposed to do them in certain circumstances, so we need both elements when we explain what a device is supposed to do. This is the function level explanation. Second, when you explain how a boat actually accomplishes its task, you need to explain how a boat actually accomplishes its task. Some boats have propellers that push the water forward, but there are other ways that a boat could get moving. Jet skis use a pump that sucks water in and then pushes it out the back. It's more pulling itself forward than pushing itself. We could use the same system to make the boat transport people and things. The key question at this level of explanation is, how will the boat transport people around? Through what series of steps will the boat actually perform its function? This kind of explanation corresponds to the algorithm level explanation. The function level is concerned with the what, and the algorithm level is concerned with the how. The function level asks, what does the device do, and in what circumstances is it supposed to do it? The algorithm level asks, how does the device actually do it? Finally, for the instantiation level, explanation identifies the physical manifestation of the algorithm. For example, let's say we choose to make a boat that has a propeller mechanism. We can make that mechanism out of metal, fiberglass, wood, etc. If we were to make a propeller out of metal, the parts would come together in a very different way than if we were to assemble it out of wood. You can cut wood with a saw and screw it together. Metal requires machine shopping and lots of different metalworking equipment. Wood and metal would also have to be disposed to different kinds of glitches. A wood engine would probably get waterlogged. A metal engine would be disposed to rust. Also note that our way of making the propeller work, which is an algorithm level explanation, could not involve combustion if we were considering making out of wood. The point is that the wood propeller mechanism and that the metal propeller mechanism could do exactly the same thing, move the boat, and it could accomplish this through exactly the same set of mechanical steps, which is the algorithm, but each instantiates the what and the how of the boat in a different substrate, and we could consider why each substrate would be a good choice for the what and the how of each engine. Those sorts of questions are what we would consider at the instantiation level. Let's bring this analogy back to the computing level, or to computing machines. Boats manipulate the physical environment. The mechanism of a boat engine turns a key into a spinning of a propeller through a series of intermediate mechanical steps. Computing machines manipulate symbols. They change one symbol into another symbol through a series of intermediate steps. Computing involves mapping one symbol onto another using an algorithm. Let's work this idea through. We said that a functional explanation says what a device does and in what circumstances it's supposed to do it. Computational devices map one symbol onto another, so a functional explanation first describes what gets mapped onto what. At the second level, it tells us what the mapping accomplishes for the system. Finally, we have to say in what circumstances the mapping is supposed to accomplish this goal. Let's say, let's take vision as an example. Certain psychological mechanisms map visual stimuli onto a response. For example, the visual look of a snake makes us jump backwards. To describe this computationally, we would say that the visual stimuli of a snake, that is my internal symbol for a snake, maps onto the symbol that stands for the reaction, jump away. Second step, what does this mapping do for the mind? Well, it's there to keep us alive. What the mapping does is avoid a potentially dangerous predator. Finally, the mapping works in the circumstance that there is really a snake there. When I see a snake in a movie, I might have the same response, but the response is not there because of movie snakes. It's there because it was a successful way to deal with real snakes. Moreover, if I didn't jump back when I saw a movie snake, we wouldn't say that my snake response device was broken. The success of that device is judged when it's working out there in the real world, when it's working in the circumstances that it was designed for. At the algorithm level, we explain how the symbol is mapped onto another symbol through a step-by-step process. In other words, algorithms compute the functions. And if we can find an algorithm, that means that the function is computable. In our example above, the question would be, how was the symbol of the snake transformed into the symbol for jump backwards? In our boat example, we said that that algorithms answer the how question. But there's a bit more to algorithms than that. We already said that an algorithm is a step-by-step procedure that tells you how to transform one symbol into another. Think of it kind of like a recipe, but it's a special kind of recipe. You know when you're cooking and the recipe says something like, cook until browned, and you think, what does that mean? Do I cook it until it's golden brown, or just starting to brown around the edges, or is the whole thing supposed to be crunchy brown? The problem with a recipe like that is it's open to interpretation. There are multiple ways to follow the instruction. An algorithm cannot be like that. There needs to be only one way to follow the instruction. Another thing that we mean when we say no interpretation is required is that it needs to lead to only one next step. So in an algorithm, you take a step and you have to be able to follow that step in only one way. But the following of that step should lead you to one and only one next step. If the instructions that you give could possibly lead to multiple steps, you haven't actually made an algorithm. So the instruction at each step needs to be unambiguous, and there needs to be only one thing that can possibly happen. Tied up with this idea is that an algorithm must lead inevitably from the input to the output. Every time an algorithm runs, it's got to do exactly the same thing and lead inevitably from the input to the output. Finally, algorithms are finite. There needs to be an algorithm for mapping. For there to be an algorithm for mapping for a function, there needs to be a finite number of steps that get you from the input to the output. We've been looking at the step-by-step procedure, but the algorithm level of explanation involves one more thing. You should also choose how the information that you're dealing with will be represented. For example, say we are dealing with a step-by-step procedure for adding two numbers together. You need to decide how to represent those numbers in a way that's appropriate for the algorithm that we choose. The number 4, for example, could be represented by the symbol 4 that we write on a piece of paper, by 4 fingers held up on a hand, or by 4 hash marks, and so on. To make an algorithm that manipulates a symbol, you need to know how the symbol represents something. We won't worry too much about the instantiation level, but you're probably familiar with at least some of the physical techniques behind computers. For example, CDs use lasers to produce and detect bumps and pits that are made on the polycarbonate layer of the disk by the lasers. However, the point to keep in mind is that a CD is a physical representation of data, whereas the function and algorithm levels explain the machine in the abstract. To summarize, here's a list of questions that you need to answer at each level in order to give a computational explanation of a process. First, what is being mapped onto what? Second, what does the mapping accomplish? Third, in what circumstances should the mapping accomplish that? These 3 questions, if you answer them, would constitute a function level / ecological level of explanation. The reason that some thinkers call it an ecological level is because we're considering the broader circumstances, all of the contextual features that might contribute to or detract from something performing a certain function. At the algorithmic level of explanation, we have 2 questions, just 2. First, how will the input and the output be represented? And second, how will we turn the input into the output in a series of steps that are unambiguous and will lead inevitably to the output? Like I said, we're not going to deal much with the instantiation level since that's really where engineering comes in and the philosophy and cognitive science side are done. But the essential question at the instantiation level is, how do we make a physical device that performs the steps described by the algorithm? For us, the algorithm is where the interest comes in, or the level of algorithmic explanation is where the interest comes in. The idea that symbols can be mapped onto one another in a series of definite steps is what makes thinking machine-like, according to the computational theory of mind. So, your homework's going to focus on algorithms. Here's a hint. Think of the strategies that your teachers showed you when you were first learning to add and subtract. Those are largely algorithms. How do those strategies represent numbers as symbols? The key to this exercise is coming up with unambiguous steps, so try to leave no room for interpretation. That is, leave only one way to follow the instructions. If you do that, you'll have a successful algorithm.